Good morning, dear students. In the previous videos, we have seen liquid vapor equilibrium, solid liquid equilibrium, and today we will see solid vapor equilibrium. Now, we all know that the process in which solid directly converts or turns into the gaseous state that the vapor form is called sublimation. Right? In the same way, if the gaseous form directly converts to the solid, it is also sublimation. The example of sublimation is iodine. Iodine is a purple color crystal when kept in a jar. This is a purple color crystal which is kept in a jar. And this jar at the normal temperature, when observed after some time, we can see that whole jar appears to be filled up with the purple color. That is, purple vapor is filled in a complete jar. So this was the solid form of crystals of iodine, and after some time at the normal temperature, this crystal of solid iodine has converted to the gaseous state, that is the vapor. When this jar is heated continuously, the purple vapor increases, and at certain point the color intensity becomes stable. That is, the formation of the crystal iodine into the vapor, and then some of the vapor, when rises up, the previously obtained or formed vapor will convert back to somewhat the semi-solid form and keeps on changing. That means both processes takes place simultaneously, opposite processes. Crystal to direct vapors and vapors to direct solid. Then we can say that the equilibrium is established between the solid I2 and vapor I2. I2, that means iodine. Iodine always exists as diatomic molecule. So I2 solid can convert into I2 vapor. In the same way, the iodine vapor can convert to the iodine in a solid crystal. Right? And this is called the sublimation. Solid to direct vapor, and that is gaseous form, and gaseous form direct solid. These are examples are camphor, naphthalene, and ammonium chloride. Camphor, you know, when we do a prayer to the God, when we do arti, we used to have kapoor in arti. You would have observed that as soon as you put kapoor in arti, it is solid cube, right? When we put it in arti flame, then due to heat, that solid should convert to liquid. But instead of that, we observe that it directly converts to the bright flame, that is the gaseous form, solid to vapor. And if that vapor is collected in a closed lid and if condensed, it will directly convert back to solid. Same thing you would have observed naphthalene balls. Naphthalene balls, when they are kept in a cupboard for the protection of the woolen cloth and silk cloth by the silverfish insects, then if your mom is putting this naphthalene ball in a cupboard, and after a month or two, if you will observe those balls again, you will either find them in a very small amount. The size would have reduced to very small balls, or sometimes you may not find that balls. Now, normally if we see that if we have kept solid thing and if it dissolves, then there should remain some liquid amount over there. But we will not find any liquid over there, and nothing is left over. It means it has vaporized in a gaseous form. And same naphthalene, when under a pressure, if it is collected in a closed chamber, they can be converted back to the solid. And another is ammonium chloride. Ammonium chloride is also a chemical compound in a solid form, powder form. When heated, directly converts into ammonium chloride vapor. And that vapor, when collected back, condensed, we will get back ammonium chloride in a crystal form. So this is the sublimation, that is called solid into vapor equilibrium. Now, let us further see the equilibrium in dissolution of solids and gases in liquids as a part of physical process. In it, here the equilibrium in dissolution of solids in liquids. Now these all we know since younger classes. When solid dissolves in liquid, up to certain extent, the solids are able to dissolve in liquid. But after some time, the solids are not able to dissolve in liquid because the space which is present in the liquid, that much amount of solid is able to dissolve in it. If more than that is applied, then it won't be able to dissolve, and we can say that the solution has attained a saturation point, or we can say that now it is saturated. So let us see that what takes place in the equilibrium establishment. When solids are dissolved in liquid, sometimes it happens that amount of solute no more dissolves in solvent. That means saturation point is attained, right? See how it happens. If a glass of water, just 100 ml is taken, and 1 by 1 teaspoonful of sugar is added, 1 by 1 teaspoon sugar, then another teaspoon sugar, right? Then another. So like this, if we add 5 to 6 spoon in it, it dissolves easily. But then it takes time if we still more adding sugar in it to dissolve. Because what happens? 100 ml water will have that much amount of molecule space in it. And whatever the space is in it, that much amount of sugar has already dissolved. So now whatever you will add, it will not easily dissolve, but it will take time. And if kept aside without disturbing, then what happens? Sometimes the sugar molecules keep dissolving. Without undisturbed, if we keep that solution aside, we'll find that some of the sugar solution will start dissolving, but at the same time, some of the dissolved will recrystallizes back. So as recrystallization takes place back, at the same time dissolution will take place. That means which was undissolved, they will start dissolving, and which were dissolved, they will start recrystallization. So two processes again takes place simultaneously. Then it is said that rate of both opposite processes, dissolution and crystallization, is equal, and here the equilibrium is established, right? See, I am asking like this: if the sugar is dissolved in the glass and a glass is kept undisturbed aside, this sugar slowly will start dissolving into the solvent. At the same time, the dissolved sugar from the solvent will start getting recrystallized back. So we can say that sugar in a solution is converted to sugar in a solid form. At the same time, sugar in a solid form is converted to sugar in a solution, and this takes place under the specific pressure. And this can be confirmed by weighing them. After preparing this type of solution, if we think that now establishment of equilibrium is completed, and if we will strain this sugar, right, sugar solution, then the solution will come back into the sugar glass, and the undissolved sugar will remain in the strainer. And if we will weigh both of them, then the amount of weighing is equal. We will say that the equilibrium is attained. Here the rate of dissolution, here the crystallization will dissolve at the same time. From dissolve, the crystallization takes place. So this will at the same rate, same speed. So we can say that at equilibrium, rate of dissolution is equal to rate of crystallization. And this is how the dissolution of solids in liquid can also attain equilibrium, or equilibrium can be established in solid liquid solution. Dissolution of gases in liquids. A very common, very best example of gases in liquid is soda water. The different types of drinks which you are all fond of, Coca-Cola, Pepsi, Thumbs Up, these are all best examples of gases in liquids. These all types of drinks are not good for our health because carbon dioxide is dissolved in it. Once in a while and in a proper amount, in a less amount, it's okay, not good. We can say it's okay, but you should not be in a practice of it. The best example, the common example is soda water. You might have heard a particular sound when the cold drink bottles or aerated drinks, we can easily say, when they are open. And if you have observed that whatever the amount of the bottle, if it is 500 ml, liter, 1.5 liter or 2 liter bottle, but top portion, somewhat portion is kept left in it because the carbon dioxide gaseous form is pressurized. That means forcibly it is dissolved in flavored liquid or solvent, and that molecules which are of gaseous in liquids, they need some space at the increase and decrease of the temperature, and for that reason somewhat less portion in the bottle is kept empty at the top portion. And so when that bottle is, when it opens, whatever the amount of gas is dissolved in the solvent will try to come into the form of gaseous as soon as they come in the contact of the atmosphere. So as soon as the bottle is opened, the atmospheric air will try to enter the bottle, and as soon as the dissolved carbon dioxide comes in the contact of this atmospheric air, they will again come back into the gaseous form. And this gaseous form gives us the fizz sound, right? So the fizz in the drink is due to dissolved carbon dioxide. When soda bottle are just opened, the dissolved carbon dioxide due to pressure, normal pressure, 1 atmospheric pressure, comes in contact of the atmosphere and so comes out as undissolved carbon dioxide, which is heard as fizz. So carbon dioxide gas is under pressure is filled as a carbon dioxide solution, and carbon dioxide solution at the effect of the pressure can convert back into carbon dioxide gas, and this is governed. This is the equilibrium. Carbon dioxide gaseous form to solution form to gaseous form at respective pressure. This equilibrium is governed by the Henry's law. What is Henry's law? The mass of a gas dissolved in a given mass of a solvent at any temperature. At any temperature, when a particular gas with respective mass is dissolved in respective mass of a solvent, then they are proportional to the pressure of the gas above the solvent. So whatever the pressure of the solvent is there, the gas which is to be dissolved, its pressure is to be little more than the solvent. This is the Henry's law, and it is because solubility of a gas decreases with increase in temperature. If temperature increases, the solubility of gas will decrease. So there won't be dissolved gas more into the solvent because temperature increases. And this is the good example that why we are drinking this aerated drinks in a cold condition. Why they are kept in a cold refrigerator. Aerated drinks are kept in refrigerator and they are also termed as cold drinks because they are inversely proportional. Gaseous solubility of gas is inversely proportional to the temperature. With increase in temperature, the solubility decreases. So when they are kept in refrigerator, when they are in a cold condition, that means a decrease in temperature, increase in its solubility. So amount of the solubility of gas in the water is more, and so it will be a highly concentrated soda water. That means amount of soda will be more, amount of dissolved carbon dioxide will be more. and therefore in a cold drinks low temperature is maintained, or even sometimes ice cubes are added. If low temperature is not possible to maintain, then ice cubes are added in a glasses of the cold drinks so that low temperature can be maintained. And if low temperature can be maintained, then low in temperature, more gas solubility increases, and temperature is decreased, solubility of gas increases, and solubility of gas increases, which means there is more soda phase in the solution, and we can have that more amount of filling of more amount of soda or the gas into the aerated drinks. So this is how the solution, that is dissolution of gases in liquids at respective pressure takes place, and which is governed by the Henry's laws. That means mass of the dissolved gas should be more than the solvent, and due to that what happens, the amount of the solubility solubility of the gas can be maintained, right? So by the time go through it, and thank you.